Hello, those who are watching in the future. It's semester 1, 2023, and this is a revision seminar for Maths 1M. And we're going to be talking about vector things and trig functions, and well, we'll see how we go. Okay. Yeah, I'll start with vector stuff first. Okay. Cool. There are a couple of different parts of the vector bit of the course, and the bit that people are always the most worried about every year are the things to do with curves and planes and that sort of thing. And so I might talk mainly about that. So the first thing I want to say is that there are a couple of different ways of talking about what vectors are doing. And if you look at different resources online, you'll get different stuff. And I think in this course they have a particular way of thinking about it, but I may do it slightly differently, and the people who run the course probably don't mind. So, so to a mathematician, a set of coordinates something like, you know, number, comma number, or so this is in 2D and this is in 3D. A set of coordinates can either represent a point, like a location, or a journey from one place to another. Something like that. So it can either be a point or a journey, and when we talk about it being a journey, it's a vector. And the word vector in English before the maths vector was invented means thing that moves something from one place to another. We talk about mosquitoes being disease vectors because they move diseases from one person or animal to another. And that is what they borrowed the word vector from when they invented the word vector. A thing that moves something from one place to another. And in physics, vectors are displacements and forces and pressures and those sorts of things, but mainly forces. That's one of the things that vectors were invented for. Yeah. And in maths, they tend to be what physicists would call a displacement, a journey from one place to another. And when we talk about a journey, it doesn't have to be from any one place to any other place in particular. It just has to be a journey that's a certain distance in a certain direction. So the thing that makes this different to any other vector is not where it is, but the fact that it's the how far it is from one place to another. And any coordinate at any moment can be either one of these. And you get to decide depending on what you're interested in doing today. So I just wanted to point that out. And mathematicians will not be particularly fussy about it if they're just writing maths down. They won't care too much because the maths will work out the same regardless of what you do. So in some high schools in the world, they will use round brackets when they mean a location and square brackets when they mean a journey. But here at this university, they do not distinguish. You just have to figure it out as you go. And the reason for that is that it can be interpreted in multiple different ways, whichever is the most useful to you. Okay, so the main thing is that if you would like to add coordinates together or multiply them by scalars, then you must think about at least one of them being a journey. That's the important thing. So you need this thing, the vector, for adding coordinates and multiplying by scalars in order to interpret what that means. Yeah. final thing to mention is that sometimes when people are feeling like they really want to use vectors as an idea, they will imagine a vector that goes from the origin to this point. And they'll call that like OP, something like that. This is the point O, this is the point P, and this is the vector OP. All right, but they may also just say from any point to any other point, and this is the vector AB, but they might also call the vector just by a letter like V or something like that. With a usually written in bold, and in bold on paper you normally underline it, but some people put a squiggle on top and some people put an arrow on top. It doesn't really matter. Some people don't put any sign on it at all to tell you that's a vector, but most of the time, if you really want someone to know it's a vector, in text it'll be in bold, and on paper people will underline it. And that's what I'm going to do. So this is the vibe. I should make sure the chat is visible so that people can tell me if something's in the chat. So that's great. And the reason I'm talking about this is partly to give my brain some time to process in the background, and partly because I'm about to do this. One of the classic and most important things to know about the way mathematicians think about vectors is that the way to make a line. So a line is a collection of points. Locations, and when I draw a line like that, there are multiple ways to tell you about how to find the points on that line. One of them is to have an equation that those points must satisfy. Okay, and so that doesn't tell you what any of the points on the line actually are, but it does tell you how to decide if they're on the line. That doesn't look like a 3 to me. So this might be the line 3 over 2x plus a half, and we've been looking at lines for a long time in maths, and so we know that that's the y-intercept and that's the slope. But the purpose of this, in its most fundamental form, is to tell you how to tell if a point is on the line or not. So if I could pick a random point, is the point 3, 7 on the line? If I pick a random point, I can go, all right, well, let's see. 3 on 2 times 3 plus a half is 9 halves plus a half. 9 halves is 4 and a half, so that's 5, which is not equal to 7, so no, it is not on the line. Yay. That's one of the points of an equation. You sub the coordinates a point in, and if it works, then it's on the line. If it doesn't work, then it's not on the line. That is what an equation is for. But there is another way to tell someone about a line, and that is to tell them what every point on the line is. So I could say that every point on the line is like that. That is the set of all of these things. The set of points with coordinates x, half plus 3 on 2x, such that x is in R. Have you seen this notation before? Okay, cool. And this is also the same line. Okay, and this tells you what every point on the line is. If I just keep picking x's, it'll just keep telling me what the points are. And this is not really that different from this at all. This is telling me that the y-coordinate is calculated from the x-coordinate in this way, which is what this says. But it's a little harder to tell if the equation of your line is more like that. Now that's quite easy to tell. If a point is on the line, sub in the x and the y coordinates, and if it comes out to -1, then it's on the line. But much harder to tell what the points on the line are. And that's one of the big ideas here, that these are the two different ways of describing how what the points on the what a set is. This is a Cartesian equation, and this is, well, I don't even know what that's called, but that's a thing. This tells you what all the points are. All right. Now, from a vector point of view, what this tells me, I'm just going to draw it again. From a vector point of view, what this tells me is it starts at the point 0, 1/2, and I can get to every other point by starting at this location and going some multiple of this journey, of going across 1 and up 3/2, because that's the slope. And that journey is the vector, I need a colour for that. That journey, that's not 1, is it? Across 1 and up 3/2. That journey is the vector 1, 3/2. So, if I start at this location and add on that journey, I will get to this location, and that will be the coordinates of a point. And if I add on half of that journey, I'll get to this location, and that will be the coordinates of a point. If I add on minus that journey, I'll get to this location, and that will be the coordinates of a point. And 7 of it will be this point over here. And so I have a journey 1, 3/2, and I can multiply it by any number I like to get a longer or shorter journey in the same direction. And then I can add that journey onto a starting point to get a finishing point, and this is all the points on the line. That idea, yep. 3/2. No. Well, that's here. After I add these two vectors together, there will be the plus 1/2. Let me show you. Now those two coordinates is t, and those two coordinates is 1/2 plus 3/2t, which is exactly this, but with a t instead of an x. Yeah. Yay, same thing. So that is another way to make a line. And I want to just talk that through just a little bit more, just to make sure we've got it. So I'm going to have to step back and do something else. Yep. Just want to point something out, is that location plus journey equals new location. So start plus journey equals end. So the point A plus the journey from A to B is the location to point B. So, and this is a location, this is a journey, and this is a location. Now you've been adding numbers that way for a long, long time. When you first learned how to add numbers, you have 8 plus 3 is 8, 9, 10, 11, and the 3 is a journey from 8 to a new place. And so one of the things that is a vector is a location, and the other one is a journey, and you get a location at the end. Some people would think about this as the journey from the origin to A plus the journey from A to B is the journey from the origin to B. They would think about it that way, but I find that difficult to process. I find it easier to say start plus journey is end. And it makes it easier for me to process this as well. Well, if if this plus this is this, then the journey must be end minus beginning. So the vector from A to B is the coordinates of B minus the coordinates of A. And some mathematicians think this is sloppy to write it this way, and other ones don't care. And most of them don't care that much. If you write them as actual coordinates, no one's going to If you write them as actual coordinates, no one's going to be able to tell whether they're journeys or locations at any point anyway, so just run with it. Okay, so since a line is a set of locations, I can make a line as a starting point plus all the possible different journeys that get to all the other points on the line. And that would be A plus, and all these journeys are in parallel directions. They're all multiples of the same journey. And so because they're all parallel, they'll all be multiples of the same journey. Like that. And so that's how to make a line. All you need is a starting point and a direction to go. And they call this a direction vector. And every line can be made in infinitely many possible ways because they've all got different places to start. There's lots of different places you could start on the line and lots of different journeys that could describe how far to go, and they will all describe the same line. So just as a concrete example, the line through the points 1, 3 and 5, 8. Even without drawing a picture of it, I can make a good imagining of how to calculate all the other points on that line. But I am going to draw a picture of it. There's 1, 3. And there's 5, 8, and I'm imagining this line here that goes through the two of them. I could choose either one of those as the starting point, and I can choose the arrow that goes between them as the direction. So I'll choose this direction, which will be the end minus the beginning. So this minus this, 5 minus 1 is 4, and 8 minus 3 is 5. That's my direction. And so all points on the line are 1, 3 plus t lots of 4, 5. But I could just as easily have chosen 5, 8 plus t lots of 4, 5, and that would have worked fine. I would just have a different set of t's that have to be minuses what they were before. And that idea is that the t lots of 4, 5 is stretching this journey out to be longer or shorter or backwards, depending on whether t is more or less than 1 or negative. And then adding that journey onto this point to get to another place. How do you feel about this? Cool. And you can do this just as much in 3D as you can in 2D. Okay, cool. And this is quite different to what I had before. So I can, if I really want to, say that this is 1 plus 4t and 3 plus 5t, if I wanted, but you wouldn't normally do that. But I just wanted to point out that that's a possibility. And no matter what t I pick, it will always produce another point on the line. And to get every point on the line, I would have to do it for every possible t. In particular, also all the half ones, right? I won't be able to get any number between here and here unless t is less than 1. So if t is a half, it'll be halfway from here, from 1, 3 to 5, 8. And if t is a quarter, it'll be a quarter of the way from 1, 3 to 5, 8. And if t is 0.9, it'll be 90% of the way from 1, 3 to 5, 8. That's really important to know. If t between 0 and 1, you get points between 1, 3, and 5, 8. Okay, cool. So this thing that I've just made, this thing just here, is called a parametric form of the line. This thing is called vector form. Parametric form and vector form are not really that different from each other. They're trying to both do the same thing and describe every point on the line and how to get to it. But I could imagine from this point here, if this was all I knew, I could imagine putting whatever formulas I wanted in these different spots here, and that would produce something else that is not a straight line, but is a curved line. It would be a curve. And so if I put any formula in this spot and any other formula here, that would produce a curve. And that's called a parametric curve. But if it's not like this, where it's number plus number times t, and this one's number plus number times t, it won't be a line. It'll be something else. It'll be like a parabola or a loop-de-loop or something like that, or a circle or whatever. It could be any number of things depending on what's in that spot. How are we feeling? Cool. Right. That's great. I will do one more thing. From this information, it is technically possible to figure out what the equation of the line is. I could figure out the slope of this arrow, and that would be the slope of the line. And then it would have to be y equals mx plus something. I could figure out the slope from this, and I could figure out the something by subbing in the 0.13 and seeing if it put the x for 1 for x and seeing if it comes out to that. But there is another way, which is to rearrange this. So I just want to point that out, but for 3D. Okay, that's enough. Just going to let myself think for a moment. Cool. So for me, this is one of the major purposes of vectors, is to be able to locate things on a line. Because vectors are straight, they're line-ish, and so that's one of the main things they're for. But the other thing is that treating them just as coordinates, I'm not thinking of them as vectors anymore, they're just really just points, and I can think of them as this is a calculation that produces a point, and different t's produce different points. Okay, so in 3D, there's just more stuff going on. I have a question here. I will talk about both parametric curves and things in 3D. Which would you like me to talk about first? You get to tell me. I'll talk about both, but I want to know what order to talk about them in. 3D, all right. Okay, vectors in 3D have 3 coordinates, or components, depending on what your thinking is. And this is called the x coordinate, and this is called the y coordinate, and this is called the z coordinate. And this is telling you a location in space or a journey in space. So it's either the location that lines up with this number on the x-axis and this number on the y-axis and this number on the z-axis, or it is a journey that's this far in the x direction and this far in the y direction and this far in the z direction. Either one of those is okay. And lines are made in the same way as they are in 2D. The most classic way to make a line is to pick a location and to pick any arrow that is a journey for between one point and another on that line. So any direction vector, and all the points on the line are p plus t times v, for t being all the numbers. And what most people do is they usually just say the line is, they usually just write that, and they don't point out that what this is saying is what all the points on the line are, and they don't point out that the t is all of the values that t could be. They just write this, but it's a shortcut, a shorthand for all of this. And this is the same thing. You start at the location P, you figure out some stretch or shrink or reverse of this arrow, and then you add that to P and it gives you a new location, and that gives you all the locations of all the points on the line. That's great. So for example, that's a perfectly good line. It passes through the point 135. Wherever that is in space, this is going to be a really bad picture. If I want to be really precise about it, I would draw an x-axis and a y-axis and a z-axis. This is going to be a bad picture, and you never have to try and draw an accurate picture of this. But here is my attempt at an accurate picture. 1 in the x direction, 3 in the y direction, and 5 in the z direction. 1, 3. So it's about there. And then it goes in the direction of -1/2 in the x direction, and none in the y direction, and 7 in the z direction. That's the journey there from that point, and then it is this line. You don't have to draw a picture like that, because you know that all lines are the same shape, they're just pointing different ways. And so it's totally okay to just draw a picture like this. This is 135, and this is the arrow -1/2, 0, 7, and the line is, that's my arrow, -1/2, 0, 7, and the line is all of these things. You're allowed to just draw it like that because all lines look the same. I'm just looking at it from exactly the right vantage point so that it looks like this. Okay, and that's great. It's lovely. And you can turn this into a parametric form pretty easily. It's just algebra now. So this is -1/2 of t, 0 times t is 0, so t times 7 is 7t, and then you can add the matching coordinates, 1 -1/2 of t, 3, 5 plus 7t. And that is what it looks like. And so the x coordinate is 1 -1/2 of t, and the y coordinate is always 3, and the z coordinate is 5 plus 7t. So either of these is a perfectly good parametric form. Officially, this is parametric form. But again, no one really cares. Your lecturer might. I'm not sure. Cool. And the way to get from parametric form to vector form is the opposite direction. You would separate it into a vector that has the numbers and a vector that has the t's, factorize out the t, and there you are. So this process works in both directions. That's great. And in fact, in the first week of Maths 1A, when you solve systems of linear equations, you'll be going from here to there. It's a thing you'll be doing. One of the reasons to get you to do it in Maths 1M is so that you can do it in Maths 1A if that's a course you're going to do in the future. Yeah, and in fact, this is a very common thing to write, is this thing, and then you work backwards to here. Cool. But what about that other way of describing what a line is? So in 2 dimensions, all you need is an equation like this to tell you what a line is. This is called a Cartesian equation. It references directly the Cartesian coordinates. That's what they're called. Named after Descartes, who invented coordinates. Really appropriately, because carte in French means map. So he was making maps with coordinates. But that is a complete coincidence. But everyone loves a good bit of normative determinism. So they're called Cartesian coordinates. Carte in French just means piece of cardboard, basically. And so a map is also a carte. It's like they call everything that's stick-shaped a baguette. Like they have magic wands in English, magic baguettes in French. So, yeah. Anyway, I've already lost it, and it's only 10 to 10. I've got two more revision seminars today. But anyway, we'll be okay. So how do you do this, but in 3D? And the thing is that lines need two equations in 3D. Two Cartesian equations in 3D. In 2D, you only need one equation to make a line, but in 3D, you need two. And it is tradition to write them like this. I do not like it. For this line in particular, I'll do it for this line, but tradition to write them like this. Something like that. So this is technically two equations. This equation and this equation. Two equations. But you could also define a line as just straight up like 3x plus 5y equals 7 and 2x minus 8. Damn it, there's a z somewhere. You could also define it just as two separate, completely separate equations. One with an x, y, and or z, and another one with x, y, and or z equals number. That would also define a line. That's a perfectly reasonable way of defining a line. It's just that this one is the easiest to turn into this. And so if your lecturers are wanting you to convert from Cartesian to parametric, they'll only give you this one. Yeah? So why is that only two equations? You need the one with x and y. It is technically three equations. You're right. Yes, there are three equations there, but you only need two of them to define the line. So any two of those would be enough to define the line. And I am going to do one more. So here's my example. I'm going to convert to Cartesian. And the way you normally go about doing this is you go, all right, I'm going to need equations that the x and the y's and the z's satisfy without referencing the t's. And so what I'm going to do is remove the t's. So I'm going to make everything t equals, and then that will do the trick. So x is 1 minus a half of t, and that would mean that, well, no, let's not do it sideways, let's do it downwards. And that would mean that x minus 1 is minus a half of t, and then if I times by minus 2, that would give me t. And that's fine. And the y equals 3 is freaking me out because it doesn't have a t in it, so I'm just going to leave that as it is. And my z equals 5 plus 7t, and so I got z minus 5 equals 7t, and so z minus 5 divided by 7 is equal to t. And since this is equal to t, and this is also equal to t, they must be equal to each other. So we get And that is a perfectly good, well, it's one of the perfectly good Cartesian equations we need. But we need two of them. And the other one is y equals 3. So the Cartesian are the reason I wanted to do this example when I noticed what was going to happen after the fact was to show that this is a possibility. It is okay to get one equation that looks like the way you expect and a whole other one which just tells you that it's equal to a constant. So this is telling me that all of the points on this line have y coordinate 3. And then this is how to figure out what the other two coordinates are. They're related in this way. And that is a thing that can happen. So it's really important to know that you are allowed to get two separate equations, and they can look like this. But if this had involved the t, I would have gotten something with y equals t as well, and then I would have just said, well, they're all equal to each other, and that would have been a perfectly good answer. How are we feeling? Cool. Right. So here's a question. If you only had one equation instead of two, what would that be? I actually want you to tell me. What if you only had one equation like this? What shape is that? It's all right not to know, but I really wanted you to think about it for a bit. It's a plane. So this is also a plane. This is a plane. Like if you take all of the points with y coordinate 3, there's 2 dimensions worth of them because there's 2 missing coordinates that you can fill in. And this is also a plane, and this is a plane, and this is a plane. And the reason why you need 2 equations in 3D is so that you have one plane and another plane, and the place where they meet is a line down there. So you need 2 equations because one equation isn't enough to make a line, it only makes a plane. So planes have one Cartesian equation. And it's always of the form, you know, something x plus something y minus something equals number. Any one of these is allowed to be 0. You can just have like x equals 3. That's a perfectly good plane equation. And it may not look like this to begin with. We've already seen one of them. This one here, up here, that's a plane equation there. And you don't have to have all of them there as well. This is still a plane in 3D, even though it doesn't mention z. It's the fact that z can be anything you want is what causes it to be a plane as opposed to a line. In 2D, that's a line. In 3D, that's a plane, because it's officially plus 0z. And one Cartesian equation is enough to tell you a plane. It's quite difficult to tell where the plane is, like what the points on the plane actually are, but if you have a random point, you can tell if it's on the plane by subbing it in. So, you know, is the point 1, 7, well, there's 3 coordinates. is that point on that plane. Let's see, 3 times 1 minus a half times minus 2 minus 7 is 3 plus 1 minus 7, which is minus 1, so no, it's not. Damn it. Ready? Ready? Here we go. If I made that a minus 1, then yes, it would be. So, point is that different numbers here will give you different planes. Cool. That's what the plane equation is for. You can actually figure out the x and the y and the z intercepts. If z and y are both 0, x is 0. Actually, this one passes through the origin because 3 times 0 minus a half times 0 minus 0 is 0. So this one does in fact pass through the point 0, 0, 0. That's where it meets all 3 of the axes. But this plane, when x and y are both 0, sorry, when y and z are both 0, x is 1. And so it passes through 1 on the x-axis. And when x and z are both 0, y is 10, and that passes through 10 on the y-axis. And it passes through minus 5/7 on the z-axis. And you can find the 3 x, y, z intercepts, and 3 points is enough to tell you where a plane is. Cool. So it is theoretically possible to make a parametric / vector version of a plane as well. I just didn't talk about it in Maths 1M. But I'm going to tell you one thing about it. With a line, you have a starting point and a direction, and that's enough to tell you the entire line. Well, planes go in 2 directions. To get to everyone on a plane, I'm going to have to go this way and that way, go how far this way and then how far that way, and that tells me a new point on the plane. So just so you know, just FYI, 137 plus t times minus 180 plus s times 0.5, 5, that would be a plane. That's the vector form of a plane. Because a plane's a 2-dimensional object, it needs 2 directions to tell you where everything is. And this would be thinking about going, here's a point 137, and I could go minus 180 in that direction and 0.5, 5 in that direction. And to get to every point on this plane, I would go some of this and some of this, or minus 1 of this and some of this, and that would mark out coordinate axes inside the plane, which is really cool. And it's one of the first things that happens in Maths 1A. But this is not in 1M, just not in there. Okay, cool. So that's great. Our lines have 2, officially 3, but really only 2 ways to describe them. We've got a T that tells you every point on the line, and so that's either parametric or vector form, and we've got an equation that you can sub things in that doesn't mention T, that you can sub points in to see if it's on the line or not. And planes in Maths 1M have only got the Cartesian version where you sub things in to tell if you're on the line. But here's the thing. Just like this equation, different pieces of it told us information about the line, like this is the y-intercept and this is the slope. Different pieces of the different kinds of equations tell you information about the object that you're interested in, if you write it in the correct way. So for lines and planes, we already know that when you write a line in vector form, this bit that isn't attached to the T is one of the points that's on the line. And this is a vector, it's an arrow that points along the line. It's not necessarily any of the points actually on the line, it is a way of getting from one point to another. So I do know that the line is parallel to this direction. And that's true in 3D just as much as this. It passes through this point and it's parallel to this direction. All right. That is definitely a thing we know about lines. A thing we know about planes is that if I pull out the coefficients of x, y, and z and make a vector out of them, that vector is perpendicular to every vector that's inside the plane. It's called a normal vector. So it's worth noting that if you have ax plus by plus cz equals d, a plane equation, then the vector ABC is perpendicular to every vector, and by vector inside the plane I mean a journey inside the plane, and they call that a normal vector. And that is a magic trick right there. It's very cool. So it works both ways. If you have the plane equation already and you would like to find a vector that's perpendicular to it, then you just pull out the coefficients of x, y, and z, and that will do the trick. If you don't already have the plane equation, but you can find a vector that's perpendicular to all of the vectors in your plane, then it will automatically be the coefficients of x, y, and z. And that is very useful and important information. But in order to use it, I'm going to need to do two other things that you can do to vectors in order to be able to use that information. No, I really mean two. Whoa, crap. Okay, it'll do. That's not crossed out, it's an underline, it's just not lined up correctly. So, things to do to vectors. The first thing to do is the dot product. So, for example, 3 naught minus 1 dot 1/2 15 6. Well, you multiply the matching bits and you add them up. So I get 3/2 minus 6, 4.5, I guess. Is that right? Great. Doesn't really tell me anything, but it's a thing you can do. And the thing that the dot product does tell you is if the answer comes out to be 0, then the two vectors are perpendicular. Or the official word is orthogonal. Did I use that in this course? That's a great word. If dot product u dot v is 0, then u and v are orthogonal. Here's a bit of etymology for you. Ortho means correct, as in like an orthodontist is a person who makes your teeth correct. And gon means angle. They are correct angle, meaning right angle. Right angle is a correct angle. So this means right in the sense of correct, and this means angle in, because gon is like a hexagon, it's got 6 angles. Yeah. There you go. Okay. And it works both ways. If they're orthogonal, then the dot product will be 0. And that's beautiful and wonderful. And the dot product actually does something even better than that. If theta is the angle between them, then cos theta is the dot product of the vectors divided by the two lengths. Do they use double lines for length in this course? Some courses only use single lines, so it's just worth pointing out. Yay! And that means that if you want to find the angle, you have to do this calculation and then do cos inverse of the answer, and it will tell you the answer. Cool. And you only ever give the answer that your calculator produces for cos inverse, because there's lots of different angles that are possible technically, but it'll give you something between 0 and 180 degrees. Where 0 if they're pointing the same way and 180 if they're pointing opposite ways. So yeah, if this calculation comes out to exactly equal to 1, that means that the two vectors are pointing the same way. And if it comes out exactly equal to -1, the two vectors are pointing the opposite way. If it comes out to 0, then they're pointing in perpendicular directions. Cool. And this is like the coolest thing ever, because the dot product was not designed to do this trick. It just sort of happened when physicists were turning quaternion calculus into vector calculus, and it just happened. It's just one of the biggest coincidences in maths that there is. And the other thing you can do to vectors in 3D, so this works in 2D, and it works in 2D and in 3D, and in 5 dimensions if you want, that's fine. There is a thing you can do to vectors that only works in 3D, which is the cross product. Only in 3D, unfortunately. And the cross product is a little harder to describe. Oh, I already drew the arrow. And it goes like this. I find it easier to write them on top of each other to do this, so I'm just gonna do this. It is extremely important to do them in the correct order because you get a different answer if you do them in the opposite order. So you've got to put the first one on the top and the second one on the bottom, and what you will do is 3 calculations, and so you cover up the position that you're in and you do this product minus this product. So 0 times 6 minus 15 times -1. That's what's in the first coordinate. And in the second coordinate, you'll do 3 times 6 minus 1/2 times -1, but it'll be minus that because it's in the middle. And the third coordinate, you'll have 3 times 15 minus 1/2 times 0. And so this one turns out to be 15, 18 plus 1/2, fabulous, 37 halves, and 45. Cool. And if your numbers here have nice big numbers like 15, this will tend to have quite large numbers in it too. Sweet. And the cross product also was invented at the same time as the dot product, and people were, the people who invented it were not planning for it to do what it did, it just happened to do it. They were trying to do calculus in 3 dimensions, like derivatives and stuff, and they invented this cross product. The cross product has the very useful and important property that U cross V is orthogonal to both U and V. That is the most useful and important property of the cross product in Maths 1M. But there is another one, is that the length of U cross V is the length of U times the length of V times sine of the angle between them. And it's not just orthogonal to both U and V, it's there's 2 directions that are orthogonal to U and V, and it is if U is your thumb and V is your fingers, then the cross product points out of your palm if you're using your right hand. Some people say if U is your pointer finger and V is your is these fingers, and your cross product points in the direction of your thumb, but it's harder for me to maintain this for as long as I can maintain this. So you can do there's my, that's my, no, that is the right hand. So if u is this and v is this, then u cross v points directly out of your palm. It's just a little easier to do than this. Yeah. Some people call this the slap rule, for like this, and it goes that way. Just slap somewhere. Cool. We had to pick a direction, and it was that direction only because that's how it turned out. Based on quaternion algebra in the 1860s. Yeah. You know, the cross product and the dot product only exists because of the complex numbers, ultimately. You know, complex numbers, you multiply by I, it rotates everything 90 degrees. And like, yeah, there's all geometry things that the complex numbers do. They tried to do that in 3D and then they couldn't. And what they came up with was the cross product. So, yeah. Okay, so one last thing, and it's specifically the thing that someone asked me about, you asked me about, which is, well, the dot product doesn't just do this thing about calculating the angle between things. The dot product does one other thing, and it is very useful to know. The dot product does this as well. If you have a line defined by a direction vector u, and your u is a unit vector, which means its length is 1. If you have any other vector starting at the same place that u starts, which is v, then I shouldn't use green. Then you can resolve u into two, this is called resolving vectors. You can make v out of two vectors, one that's in the same direction or possibly the opposite direction that u is pointing, and one that is perpendicular to the direction that u is pointing. All vectors can be broken up in those ways. And this distance here, that distance is u dot v. So if I have a unit vector and I try and find how long the part of v that's in the same direction of u is, that distance is u dot v, as long as u is a unit vector. And the reason it works is because of, actually no, well, it's all related to this thing with the cos theta. If u is a unit vector, then the length of u is 1. And cos theta, if the theta is there, this distance will be that distance times cos theta, because that's how right-angled triangles work. Yeah. So because of this, the projection of v onto u is, if u is a unit vector, it is definitely something that's in the same direction as u, right? Because it's on this line. And so it has to be something times u. And u is a unit vector, and if I want to make the vector this long, I should multiply by that length. So that's what it is for unit vector u. But if u isn't a unit vector, I might even write it as v dot u if that's okay. But if u isn't a unit vector, I'm going to have to make it a unit vector first, and so I have to divide this and this both by the length of u, which means I have to divide by the length of u squared. And so projection of v onto u is v dot u divided by the length of u squared times u for any vector. So it was designed first for unit vectors, and then this will adjust it to work for any vector at all. So just note that all of the vectors in this calculation are u except that one. Yeah. So just as an example, no, I'm not going to make it hard for myself by putting fractions in. The projection of 108 on -162. So first I would need to do, I need to find the length of this, because that's the one I'm going onto. So that's in my head, this is the u, and this is the v in the formula. I need to find how long this is. And when you find the length of any vector, it'll be the square of all of the coordinates added up and then square rooted. Oh man, okay, so we've got 1 plus 36 plus 4, square root of 41. Cool. Sure. Great. All right, and we technically don't need to square root that. Oh, that would have been quicker, wouldn't it? There we go. I only need the length squared anyway, so there's no point square rooting it and then squaring it. Cool, and then the dot product of 108 and -162 is -1 plus 0 plus 16, which is 15. And so therefore, the projection is, so it is this divided by this. So the dot product divided by the length of u squared times the vector u. Cool. I mean, I guess. 6 times 15 is 90. If I really want to, that's what the vector is. And what that means is that if I want to follow this vector all the way up to the point where I could go right angles to get to this vector, this point, to get to this vector, I would have to go this far before I turned at right angles. Does that answer your question? Yeah. Cool. And so that's what dot products are for. At this time, I'm going to be quiet for a moment and let you ask questions or just think. Yep. It's grammar. So how do you know which one to use? It's a projection of this one onto this one. So since this is the onto, that tells you it's the u. Maths is at least a proportion grammar. Statistics is at least a quarter grammar, but the rest of maths, grammar is the thing. And having the prepositions are the thing that you need to look at. They may not use the word onto, they may just use the word on, but it means the same thing. I've never heard them use the word at in that context, but I presume it would have the same meaning. Okay. So here's the thing. I'm just going to do an example now, which is the one that I've been specifically asked about. So just some examples. Find the plane through the point 1, 1, 3. Parallel to the plane with equation x plus 7z equals 8. Okay. So I know two things about plane equations, well, several things. Plane equations are Cartesian equations, it's going to be something s plus something y plus something z equals something. I also know that if a point is on a plane, when you sub it in, it'll work to the equation. And I also know that a line, a vector that is definitely perpendicular to the entire plane is the normal vector. So if a normal vector is perpendicular to one plane, it has to be perpendicular to any plane that's parallel to it. So this is my picture in my head here. There's a plane, and there's another plane that's parallel to it. And if this vector is perpendicular to that, then it's perpendicular to this too. So that's the picture in my head. So parallel planes have the same normal vectors. That's really useful to know. And in fact, parallel planes therefore have the same this bit of the equation. So the plane must be x plus 7z equals something for some other number d. So if you want a plane that's parallel to another plane, well, this bit has to be the same, or at least a multiple of each other. It would perfectly well if it was 2x plus 14z equals something. That would work too. It just has to be a multiple. So that's one thing I know about planes. If this bit's the same, then they are parallel. And the other thing I know about planes is if this point 113 is going to be on this plane, then when I sub this into there, it should work. So the point 113 is on the plane. So 1 plus 3 times 1 must be equal to d when I sub it in. No, 1 plus 3 times 3. Damn it, what am I doing? Making up crap entirely. X plus 7 times z equals d, and x is 1 and z is 3. Okay, x plus 7 times 3. And so d is therefore 22. So the equation is x plus 7z equals 22. Yay! All right. Yeah, let's do that. That'll do. Find the plane. Let me just check. But that point is not on that line. Okay, cool. It won't work if the point's on the line because then there's lots of different planes. So Find the plane through the line with the equation x minus 1 is equal to y plus 2 over 3, which is equal to z, and the point 0, 0, 5. Well, I know that the way plane equations work is that if I had a normal vector, I would be able to find the x, y, z part of the equation. And so that's my goal, find a normal vector. And if I have any one point in the plane, I can do the same thing I did here and it'll tell me what the number part is. And so I need a normal vector and one point. That is what I need. And so, this is the picture in my head. Here is the line and here is the point 0, 0, 5. And there is the plane that goes through the two of them. That's probably a bad picture, but anyway. Cool. If I had two vectors that were in the plane, I could cross them to figure out a vector that's perpendicular to both of them and therefore perpendicular to the entire plane. And so to get a normal vector, two vectors in the plane crossed should produce a normal vector. And currently I have no vectors in the plane, but I do have a line, and lines have vectors on them. And since that line is in the plane, all the vectors on the line are in the plane too. So I'm going to find a vector from that line. Okay, there are two ways to approach this. One is to guess some points on the line and subtract them, and then you have a vector on the line. And the other one is to convert this to vector form because it has vectors that are on the line. So I'm going to say that x minus 1 is t, and y plus 2 on 3 is t, and z is t. And so this is telling me that x is t plus 1, and y plus 2 is 3t, and so y is 2 plus 3t. No, sorry, 3t minus 2. What am I doing? And this is still z equals t. And so the points on the line are t plus 1 for x, and 3t minus 2 for y, and t for z. And I can separate that into something with the numbers 1 and minus 2, and this one doesn't have a plain number, so I put 0, and something with the t's, t and 3t and t, and so that is 1, minus 2, 0, and t lots of 1, 3, 1. I can factorize out the t out of the three different coordinates there. And this is now the vector form of the line. And so now my picture goes like this. I have the point 1, minus 2, 0 is on the line, and I have the arrow 1, 3, 1, like the vector 1, 3, 1. We also have separately the vector 0, 0, 5. So I have one vector in the plane, which is the vector 1, 3, 1. I need a second vector in the plane, which means I should subtract these two to get a second vector. So 1, 3, 1 is a vector in the plane. Second vector would be end minus beginning. It doesn't really matter which way around I do it. I shall do that, and that is now minus 1, 2, 5. And that's this vector here. And those two vectors I can cross to find the normal vector. Well, a normal vector anyway. So 1, 3, 1 cross minus 1, 2, 5. So 3 times 5 is 15. Minus 2 is 13. I'm just going to do that. And 1 times 5 is 5. Minus 1 is plus 1, and I'll have to minus that. And 1 times 2 is 2. Minus 3 is that. And so I've got 13 minus 6, 5. All right, doing well. And now, since this is a normal vector to my plane, the equation is 13x minus 6y plus 5z equals some number d. And now I'm at the same stage I was before. I can sub in any one of these points and it'll tell me what d is. Sub in 0, 0, 5. That seems like the easiest one to sub in because it's got lots of zeros in it, since it's on the plane. And so I've got 13 times 0 minus 6 times 0 plus 5 times 5 is d. And so d is 25. And so therefore the equation is 13x minus 6y plus 5z is 25. And if you wanted to be absolutely certain that you had done it right, if you subbed in any other point that you know is on this line, it should give you the same answer for d. So if I had subbed in the point 1 minus 2, 0, well, 13 times 1 minus 2 times minus 6 times minus 2 is 13 plus 12, which is also 25. So that works out well. All the points on this plane will give you the same answer for d because that's the point of the equation, and it comes out to the same answer for every point. So I believe that it is good. How are you feeling about that I went through? So if you're going to tell people, show working for this, it's really useful to tell them when you're about to calculate a normal vector, and tell them when you're about to sub something in. It's not important, but it does make it easier for them to read, and a person who finds your thing easy to read is happier and therefore more willing to give marks. Happy markers are generous markers. Yeah. Cool. There are lots of other things you can do, but they all fall down to that same idea, is to make a line. You need 2 points on the line, but what you really need is a point and a vector for a line. And what you need for a plane is a point and a vector that's perpendicular to the plane. And to make a vector that's perpendicular, you can cross 2 vectors that are in it. But you can also just be straight up told what that vector is to begin with. So just be careful, you don't have to do a cross product if they've already told you the vector that's perpendicular. So think carefully about whether you've already got the vector that you need that's perpendicular. All right. The only other vectory thing in this vibe, as opposed to vector proofs, which is a whole other thing, the only other vectory thing in this area is the parametric curves. They're really a thing of their own, but they are not, at their fundamental level, they are not different from trying to do the parametric version of a line. You've got a number t that tells you where you are at every point. And the t has various options for what's allowed. So for a line, t is all the possible numbers. But for a parametric curve, it's usually only a particular zone of possible t's you're allowed to use. And as the t moves forwards, so in this one, And when t is 0, I'm here, and as the t gets bigger and bigger, I move this way. And then that's where t is 1, and then I keep going this way. I mean, if t was negative, I'd be going this way. And parametric curves are the same thing, it's just that it's not so easy to tell what the thing looks like from the graph. I'm going to talk about it for just a... So parametric curves have some function of t in each coordinate. And in 3D, you can have 3 coordinates, each with a function of t. And the idea is that this is all the options for t. And then here we are in 2D. And as t moves forwards, each value of t produces one of the points on this curve. So this value of t produces that point, and this produces that point, and maybe this produces that point, and maybe this produces that point, like that. And at different t's, as t moves forwards along here, this moves around the curve. And it doesn't have to be going at this, this will go forward at the same speed. If this goes forward at the same speed, this doesn't have to always be going the same speed. As you can see from here, it goes quite slowly here, but from here to here it actually goes quite slowly here, but from here to here it goes very quickly to get from that point to that point. So it's possibly not going at the same speed at every place. And there's 2 things that they've sort of been interested in your course, and one is to figure out, well, any object in the plane probably has an equation involving only x and y that tells you whether you're on the path that this thing follows. So there are 2 questions you want to ask. What's the equation, the Cartesian equation, that tells you whether you're on the path or not? So something involving just x and y, or in 3D x, y, and z. But x and y, I don't think they do it in 3D, this question, that says you're on the path, and so involving x and y. And the other question you can ask is, what direction am I facing at any point as I travel along the curve? That's the tangent thing. Which is the same as asking, where is the tangent? So what I mean is, if I was here, if I was a very small animal living on this curve, I would be facing, as I come past this point, down there. And that is the same direction that the tangent's going. Whereas over this point, I'd be facing that way. That's the direction the tangent's going. So that direction is a vector. And its slope is the slope of the tangent. And so if you can figure out the direction vector at any point, you can do its y coordinate divided by its x coordinate, and that gives you the slope. So for that Cartesian equation, it's easiest to do as an example. This is one of them. So the goal is the same as it was for ordinary lines. which was to turn this somehow into something that involves only x and y. So the x is t squared plus 1, and the y is 3 minus 4t. So you've got two choices. You can try and make everything equal to t and then go, well, since they're equal to t, they must be equal to each other. Or you can make one of them equal to t and sub it into the other one, which is usually the easiest way of dealing with it. And so I can see from the second equation, from number 2, 4t is equal to 3 minus y. So t is a quarter of 3 minus y. And so I can sub that into the other one. We had x equals t squared plus 1. And so x is equal to a quarter of 3 minus y squared plus 1. And that is a perfectly good Cartesian equation. I can stop there if I want. There's no particular reason why I have to expand it out. I mean, I feel uncomfortable with the quarter inside there, so maybe I'd do like 1/16 of 3 minus y squared. That makes me feel slightly better, but there's no particular reason to continue. I can just stop there. Perfectly good Cartesian equation. Now, I don't know which bit, if t is only going from 0 to 1, I don't know which bit of this curve it is, but it's right. I will also point out this is a parabola. If it was y equals something with an x squared plus 1, that would be a parabola going this way, but it's actually going to be a parabola going this way somewhere. I don't know where it is. Oh, not that way. Actually, I know what the vertex of that parabola is. The vertex is at the x-coordinate is 1 and the y-coordinate's 3. That's fun. Something like that. I didn't mean it to be a parabola. It just is. And so I don't know which direction it's going as t moves forwards, around that way or down that way. Okay, so let me just figure out where the tangents are. Okay. So if you differentiate this to get two derivatives, that vector will be the direction that you're facing at every different t. So I'll just call it x and y equals. So the derivative, which is dx on dt, dy on dt, is 2t for that first coordinate and minus 4 for that coordinate. So that's telling me that when t is 0, it's going in the direction of 0 minus 4, and when t is 1, it's going in the direction of 2 minus 4, and when t is 10, it's going in the direction of 20 minus 4. Different values of t will give you different arrows, which is what the direction that we're going. So I can see here that must be t equals 0. When t is 0, I get the point 1, 3, which is this point here. And the direction that it's going when I'm facing that way is 0 minus 4, which is downwards. So it must be coming round here. So just as an example, when t equals 1, the point is 1, sorry, not t equals 1, t equals 0. The point is 0 squared plus 1, 3 minus 4 times 0, which is 1, 3. And the direction is 0 minus 4. And so what that's telling me is that here at the point 1, 3, it's going that way, 0 minus 4. So I was thinking it's going round the curve this way. And you'll notice that that tangent is perfectly vertical. And the tangent being perfectly vertical will correspond with the x-coordinate being 0. And the tangent being perfectly horizontal will correspond with the y-coordinate being 0. And the tangent being like a weird point that doesn't have a tangent will go with them both being 0 simultaneously. Because that's telling you that at that point, the direction you're facing is 0, 0. You're not facing anywhere. There is no direction that you're going. You have actually momentarily stopped at that point. Yeah. And so the slope, I'm just going to do another one. In t equals -1, the point is -1 squared plus 1, 3 minus 2, 7. And the direction is 2 times -1 minus 4, which is -2 minus 4. So that's over here somewhere. It's going that way, like that. Actually, sorry. Anyway, something like that. And the slope of this line is y divided by x, which is 2. It's got a slope of 2. So yeah. And so just pointing something out, they'll go something like dy on dx, which is the slope of the tangent, is dy on dt divided by dx on dt. That's how they're doing it. And which is what the coordinates of this was. That's dy on dt and that's dx on dt. I'm just going to add one thing here. This is a vertical tangent. So there was a classic Mobius where they gave you a weird-ass thing like this and asked you where are the tangents vertical, horizontal, and neither. So you had to find all the places where the first derivative is 0, and all the places the derivative of x is 0, and all the places where the derivative of y is 0. And then the ones that they shared, there's no tangent. The ones that only derivative of x is 0, that's when it's vertical. The ones where only the derivative of y is 0, that's when it's horizontal. So just point something out. It's like this. dx on dt equals 0 and dy on dt equals 0, and they're both 0. And so you'll get all these different answers for t, right? And so these are vertical tangents. These are horizontal tangents. And these are no tangents. Yeah. And it's a useful way of thinking about how to do it is to make a big list and go, well, the ones that are in both lists are where there's no tangent. The ones that are only in one list are the ones where it's like that. And there's all these other points where neither of them is 0, and they're the ones where the tangent's neither vertical nor horizontal. It's a nice, perfectly good sloping line. Okay. I did want to do one final example of making the Cartesian form. This may be bad. It may not turn out very well at all. That's cos t and sin t cubed. This is going to suck, actually, isn't it? All right, let's do that. I know for sure that cos squared plus sin squared is 1, and that is a very nice way of getting rid of the t's. And so that would mean this is going to be awful, isn't it? I've really made it hard for myself. I don't like making these examples up. Make it a 4. It would be really nice if you could change your exam question halfway through. That'd be great. But it's not the worst. I just want to point something out to you. It is not the worst plan if you don't know what to do. At least you're proving that you know how to do things. So, so if you can't actually solve the problem they've got, say, I don't know how to solve this problem, but I can solve this one. And if it makes a difference between passing and failing, or between a credit and a distinction, they'll give you a mark, right? Not all the marks, but one, right? All right, I've got the squared here. If I square it, I'll get the 4 that I'm looking for. And that is 1 minus 2 lots of sine t squared plus sine t squared, which is to the power of 4. Crap. This I do not like. That's okay. I can fix it. So I do know that x is equal to 3 cos t to the 4. And so x on 3 is cos t to the 4. So I can sub in that there. And I do know that sine t y is sine t to the 4, so I can sub that in there. And I guess if I square rooted it, that'll be sine t squared. And so now I can sub them all in and get that is x on 3, and that is root y, and that is y. Yay! Cartesian, all the t's are gone. Possibly not the quickest way, but a way. If I had made it cos squared and sine squared to begin with, everything would have been much neater, and I could have subbed everything in. All right, that'll do. 75. Wow. Any other thoughts or questions on this stuff? Cool. All right. I know there's only 5 minutes to go, but I may go over. I am not offended if you leave, but I did want to talk a little bit about trig functions because it was one of my... Just to do the exact questions that I've got asked a couple of questions about. So I might just do straight up a couple of examples instead of doing an overview to begin with. Do they write this symbol? Like that? Is this a thing that they write in this course? Okay, cool. So solve sine of 2x is equal to a half for x between in the interval from minus pi to pi. Okay. There are at least a couple of ways to do this, but I'm going to show you one. Well, no, before I even do it, I want to draw a picture of this. The angle 2x, whatever it is, its sine is a half. Here is my unit circle, and it's telling me that the angle 2x, which is measured around the edge of the unit circle, has sine being a half, and sine being a half, well, sine is the y coordinate. And so I've confused myself by using x for both the angle and other things, but that's okay. There's a half there, and this is one of the points. If this is 2x, then sine of 2x is a half. But there'll also be another one over here on this side, where the y-coordinate is also a half. And then I suppose if I went backwards this way, that would also work. Or if I went all the way around like 16 times and got to here, that would also work. There are many, many different answers. And so what I'm going to do is I'm going to figure out what all of them are and then narrow them down to the ones that x is between minus pi and pi. So first I'm going to find one of the answers. So one solution is that 2x is the inverse of, sine inverse of a half. Some mathematicians write this as arc sine. So if you're very good at memory, or even slightly good at memory, you will know what that angle is. I can't know it without drawing a picture, so this is what's going on in my head. The classic numbers come from equilateral triangle cut that's got edge length 2 and it's cut in half. That would be 60 degrees there, that's 30 degrees there. Sine is the opposite over the hypotenuse, so that would be pi on 6. That's the 30 degree angle there. I could also ask my calculator. So it's in radians. I'm just going to put it in degrees because the classic angles are in degrees. I believe that's in the setup, 3 degrees. Okay, so sine inverse of 1/2 is 30 degrees, which is pi on 6. Awesome. But if you had it in radians, which is probably a good idea, it gives you this answer. If you want to know what fraction of pi it is, divide it by pi. Yeah. That's a 1/6, isn't it? Yeah, okay. That is a 1/6. Cool. If it had been 0.333333, I would have known it was a third. Okay, so 2x is pi on 6. So one of the answers is that 2x is pi on 6. Okay, I'm not going to go all the way. X is going to be pi on 12 eventually. But that's only one of the possible answers. The other answers are, there'd be one over here as well. And so this is pi on 6 here, which means this is pi on 6 here. And so we have other solutions. 2x is, we have pi on 6 was one of them. But we also have pi minus pi on 6, which is 5 pi on 6. So this is the pi on 6 here. And then there's a pi minus pi on 6, which is the 5 pi on 6. So that's the pink one in the picture. And this is the blue one in the picture. And then, you know, any multiple of 2 pi away from there would work just as well. So I could have well, just nearly there. Like that, for any integer k. And so my x would be pi on 12 plus pi k and 5 pi on 12 plus pi k. That is all the possible answers, completely ignoring the allowable x's, which is between minus pi and plus pi. And so now I just need to find all of those angles. I'm going to draw a new diagram. So pi on 12 is quite small. We've got to cut this into 12 pieces, which means cutting this into 6 pieces. It's about there. There's pi on 12. And we have 5 pi on 12, which is 90 degrees away from there. Because it's 5 pi on 12 It's just a little under half, isn't it? Okay, so that's about here, because 6 pi on 12, so there's my 5 pi on 12. And then I can go pi away from any of those. So pi away from here is here. So there's my pi on 12 plus pi. Oh, but that's too far. That's gone beyond pi. So I should go, damn it. So if I go pi forward from either of these, I go past the pi level. So I need to go back pi from here. And so that's going to be minus pi plus pi on 12. And there'll be one here as well, which is about there. 180 degrees from there. So that's minus pi plus 5 pi on 12. And so, whoa, 4 answers. 4 answers between the zone from here to here and the zone from here to here. So x is equal to pi on 12 and 5 pi on 12 and minus pi plus pi on 12 and minus pi plus 5 pi on 12. Whatever all of those answers are. I guess I could put them all in proper fractions if I want, I suppose. 12 minus 12 pi on 12, so that's minus 11 pi on 12. And 12 minus 12 plus minus 7 pi on 12. Cool, they're my 4 answers. That is a way of doing this. There is another way, which is to say that if x is between minus pi and plus pi, then 2x would be between minus 2 pi and plus 2 pi. And so I could have pulled in the ones between 2 pi and plus 2 pi from here, and then divide them all by 2. That's the other way of doing it. How do people feel about what I just did? It's complicated, but I picked one that was complicated. Yeah. So I think it's just for myself. I'm going to talk through the stages. I found just one of the answers, which was from the sine inverse, and then I found the 2 answers that would fit into the top half, and then I went to all the other answers by adding the 2 pi k, and then that got me all of these, and then I imagined where they were and which ones were within the minus pi to plus pi. And to do minus pi to plus pi, I have to go from 0 to minus pi this way and from 0 to pi that way. Okay. Cool. That was solving that. Does anyone have any other tricky questions that they want me to do? It's okay if not. I will say a couple of things. As you move around the unit circle, this may be something that you all know, but I'm just going to do it anyway. Cos is positive. Cos is the x-coordinate of the point on your unit circle. And the x-coordinate's positive over here. And sine is the y-coordinate of the point on your unit circle, and the y-coordinate is positive here. And tan is the slope of the point, the line that goes from the origin to your point on the unit circle, and the slope is positive here. And I know a lot of people remember the ASTC thing, but I am much more visual than that, and I have real trouble remembering the correct order of letters. I don't know if you've been watching closely, but I don't always write on the page the first letter of a word when I start writing it. And so if you are also like me and have trouble remembering which order letters go, you may find it easier to remember these pictures. That cos is positive on the right-hand side, sine is positive at the top, and tan is positive where the slope is positive. That might be helpful. But I'll also say that sine inverse produces angles here where cos is positive. And cos inverse produces angles here where sine is positive. that's kind of cool to know as well. And the reason for that is that they have to produce all the angles within 90 degrees, because that would be silly if they didn't, because they're designed for doing right angle trigonometry. And they have to produce all the other answers that cos produces. I can't go this way because all of those angles have the same answers for cos as these ones do because it's the x-coordinate. So I have to go that way. And that gives me the other angles. All the answers for what cos could be are all the x-coordinates. And so the angles have to be these angles because they cover all the x-coordinates of all the points on this unit circle. And sine inverse has to cover this, and all the other x-coordinates, all the other y-coordinates are covered by going this way. And tan does the same job. Tan inverse produces these answers as well, because all the slopes are produced by both of these. I could technically have gotten all the slopes by going that way for doing tan, but we had to pick something. So we picked the one for sine because it's the one that's on the top of tan. Tan is sine divided by cos. I don't know if that helps as a mnemonic, but it helps me. And this will come back again in Maths 1A when you do the derivatives of the inverse trig functions. Yay. Cool. I'm going to stop there.